Dear students, good morning. Again, I welcome you in this online class. In a series of lectures, we have discussed the development of nuclear physics and properties of nuclei. And in continuation, today I am going to discuss the important semi-empirical mass formula. Scientists developed this nuclear drop model to give physical insight into nuclear properties. In this model, nucleus is assumed like a liquid drop in which nucleons are closely packed. For expressing the atomic mass in 1935, von Weizsäcker developed a formula which is known as semi-empirical mass formula, in which certain properties of classical liquid drop is used. Binding energy of the nucleus is given by EB equals to Z into proton mass plus A minus Z into neutron mass minus atomic mass into C square where m atom is the mass of the neutral atom. Now we discuss the various terms that contribute in the binding energy. The important term which contribute in the binding energy is volume energy EV. This term is based on saturation properties of nuclear forces. Nuclear forces among nucleon are very strong and have very short range, about 3 fermion. We can visualize each nucleon as a sphere, and these are assumed to be closely packed, in which each nucleon touches the 12 neighboring nucleons. It can be assumed that interaction between any two nearest neighboring nucleons resulting in certain interaction energy. Total interaction energy of such type depends on number of adjacent pairs of nucleons, that is, depends on the mass number, that is, the total number of nucleons in the nucleus. Since volume of the nucleus is directly proportional to A, so this type of interaction energy is related to volume of the nucleus. Attractive nuclear force results in negative interaction energy, but binding energy is taken as positive. Hence, binding energy corresponding to this interaction can be approximated as volume binding energy EV proportional to A, and if we make it equal, in that case this volume binding energy EV equals to AV into A, where AV is a positive constant. The next term which contributes in the binding energy is surface energy ES. Nucleons on the surface have fewer neighbors and they are not completely surrounded. The nucleon on the surface feels attractive forces only from one side, whereas the nucleon in the interior feels attractive forces from all sides. In the volume energy term, it was assumed that each nucleon interacts with other nucleons equally from all sides. So, a term that is proportional to the surface area of the nucleus must be subtracted to reduce the binding energy. This negative correction constitutes the surface energy term ES, which represents the loss of binding energy And as I have told, this binding energy is depends on the surface area, and this nucleus is assumed to be spherical in shape. So Es is proportional to R square, and if you make it equal, in that case Es equals to minus alpha R square, or Es equals to minus As A capital A raised to power 2 by third, because R, the radius of a nuclei, is R0 A raised capital A raised to power 1 by third. Since lighter nuclei have greater fraction ratio of number of nucleons on the surface to those in the interior volume, so surface energy term is the most significant for lighter nuclei. The third term which contributes in the binding energy is Coulomb energy. Coulombic repulsion force between protons is long range force. The Coulomb potential energy of jet protons packed together in spherical symmetric manner is proportional to number of proton pairs, that is z minus 1 by 2, and is inversely proportional to nuclear radius. The contribution to the binding energy is expressed as Ec proportional z minus 1 upon R, and if we make it equal, in that case Ec equals to minus Ac z minus 1, and as I have told earlier, R is equals to R0 A raised power 1 by third. That's why this Ec equals to minus small ac z minus 1 upon A raised to power 1 by third. The Coulombic repulsive energy term lowers the binding energy and increases the mass. Hence, it opposes nuclear stability. For heavier nuclei having Z greater than 1, hence Ec can be approximated as Ec equals to minus Ac Z square upon A raised power 1 by third, means this Z into Z minus 1 can be approximated as Z square. The next term which contributes in binding energy is the asymmetry energy. The asymmetry energy Ea arises due to unequal number of neutrons and protons in the nucleus. To get the best agreement with predicted binding energy, it can be written as Ea equals to minus Aa n minus z whole square upon A. Here n minus z represents the neutron excess, and this can also be written as Ea equals to minus Aa A minus 2z whole square upon A, because n equals to A minus z. So by substituting n equals to A minus z, we get A minus 2z whole square instead of n minus z square. The contribution of the asymmetry energy to the binding energy is negative because it decreases the binding energy of the nucleus. This correction term cannot be understood with simple liquid drop model. It is a purely quantum mechanical effect which is related with nuclear energy levels. To be in the stable state, nucleus should occupy the lowest energy state. The asymmetry energy is 0 for Z equals to n, and as this neutron axis rises, this asymmetry energy rises, and that results in greater stability of the nucleus. The next term which contributes in binding energy is pairing energy. The nuclei having even number of both protons and neutrons are strongly favored and most stable in nature, whereas nuclei having odd numbers of both protons and neutrons are the least stable. Hence, this pairing effect, that is spin consideration, is taken in the pairing energy, which can be expressed empirically as EP equals to plus minus 0 AP upon A raised power 3 by 4. The pairing energy is positive for even nuclei and 0 for odd even nuclei or even odd nuclei, and negative for odd nuclei. That is, if both Z and N are even, in that case EP is positive, so EP equals to AP upon A raised power 3 by 4. If Z even and Z, or odd Z and N even, in that case EP equals to 0, and for both Z and N odd it is negative, so EP equals to minus AP upon A raised power 3 by 4. Here AP is assumed an approximately constant coefficient. The total binding energy of a nucleus of atomic number Z and mass number A is written as the sum of all these energies, that is binding energy EB equals to volume energy plus surface energy plus Coulomb energy plus asymmetric energy plus pairing energy. And that's why this semi-empirical binding energy formula becomes EB by substituting the values of all terms EV, ES, EC, EA and EP as we have discussed above. This EB becomes AV into capital A minus AS, capital A power 2 by 3rd minus AC, Z minus 1 upon A raised to power 1 by 3rd minus A minus 2Z whole square upon A minus plus minus or 0 AP upon A raised to power 3 by 4. And the atomic mass M atom equals to, that is the sum of proton mass plus sum of neutron mass minus this binding energy. So that is MA Z equals to Z MH plus A minus Z Mn minus EV by C square. And this semi-empirical mass formula becomes in empirical mass formula by substituting the values of EV and M atom, it becomes Z MH plus A minus Z Mn minus 1 by C square AV into A minus AS A raised power 2 by 3 minus AC ZZ minus 1 upon A raised power 1 by 3 minus A minus 2Z whole square upon A minus plus minus 0 AP upon A raised power 3 by 4. A set of constants AV, AS, AC, AA and AP have been determined as AV equals to 14.1 MeV, AS equals to 13 MeV, AC equals to 0.595 MeV, AA equals to 19 MeV, and AP equals to 33.5 MeV. Other set of constants have also been developed by empirical fitting the observed mass. This equation is known as the semi-empirical mass formula because the constants, all the constants AV, AS, AC, AA and AP are determined empirically by fitting observed atomic masses. The semi-empirical mass formula predicts the binding energies which are remarkably close to the observed values except those of very small a. The discrepancies between predicted mass value and observed mass values are the least. And that's all in today's online lecture. Thank you.